Welcome. So this question says, what is the reactance of a 7 Henry inductor when a 5 radian per second AC voltage is applied across it? So here we have our inductor, and it's L, and that equals 7 Henrys. And we have a EMF. Of course, we should have some resistance in there, but we're thinking theoretically, so we'll just ignore that. And let's have a look. The frequency is 5 radians per second. So it's not mains, it's 5 radians per second. So my XL is my reactance, inductive reactance, and it's basically measured in ohms. It's a frequency dependent resistance. And my XL is equal to omega L. So my XL is equal to my angular frequency, which would be 5 times my inductance, which is 7. So XL is equal to 35 ohms. And to give you, just let's visualize this. If I plot a graph of frequency, omega, say frequency, in radians per second, and I plot that versus my inductive reactance, which is my frequency dependent resistance. It's a linear expression, so it just increases with frequency. High frequencies, much more resistance. Low frequencies, much low resistance. At low frequencies, it's like just a long piece of a very conductive wire. At high frequencies, all the magnetic effects come in because you're changing the current flow very quickly. So that makes sense. If I look at the next bit, it says, what is the resistance of a 10 ohm resistor when a 12 radian per second AC voltage is applied across it? And so here's my AC voltage source, and here's my resistor, and this is R, and this is 10 ohms, and this is 12 radians per second, so it's a different frequency. I don't use the term reactance, I use the term resistance, and that's significant because reactance is the term I use for frequency dependent resistance, and resistance is the term I use for traditionally for non-frequency dependent resistance. It's just the resistance. So what I have to say is that my resistance equals my resistance. There's no frequency effect. So my resistance is going to equal 10 ohms at any frequency. So if I plot my R versus my frequency in radians per second, I just get a constant value. It doesn't care. It's just going to stay at the same value. And then my third part is, what is the reactance? Again, we're back to reactance now. What is the reactance of a 1 farad capacitor when a 4 radian per second AC voltage is applied across it? So here's my visualization of my circuit. I'm ignoring the fact there's, really always will be a little bit of resistance, but I'm just saying how, imagine we only have capacitance. My capacitance equals 1 farad, and then this was 4 radians per second. And so now I say, well, my XC is equal to 1 over omega C. So my XC is equal to the 1 over my omega is 4. My C is 1. XC is equal to 1 over 4, which equals 0.25 ohms. They're all measured in ohms. And if I want to visualize this, I would put XC versus the frequency, and I'm measuring the frequency in radians per second. I put my frequency as omega to tell you it's an angular frequency. And this is going to be like that. So at high frequencies, my resistance, my frequency dependent resistance gets less and less and less. And at low frequencies, yeah, it's like an open circuit. And so my frequency dependent resistance gets higher and higher and higher. If I wanted to do this problem using Hertz, so supposing I wanted to use Hertz instead of radians per second, then I would convert from, I'd say, well, my omega equals 2 pi f. So from that, I'd work out what my omega is, and then I'd put my omega into my XL and my XC. I can't just substitute frequency in Hertz for frequency in radians per second. This expression is written as omega because it has to be the frequency in radians per second. You can substitute in 2 pi f for the omega because that's numerically the same value, but you have to get to the radians per second in order for this system to work. So there we have it.